In section 10.1, we learn about curves defined by parametric equations, which essentially means that instead of thinking of y as a function of x, x is the input and y is the output, we're thinking of x as some function of t, like x equal g of t, and y is also some function of t, where t is the parameter. You've actually worked with things defined using a parameter before. Back in Math 60, when you were looking at related rates, that was a bit of an idea of working with a parameter. If you had, like, the area of a circle is equal to pi r squared, you could find the rate of change of the area related to the rate of change of the radius with respect to time. This is something that you would have done back in Math 60. So we're doing a similar thing here. Back in Math 60, you would have thought of the area changing with respect to time and the radius changing with respect to time. Now we are thinking of, just in general, x as a function of t. T doesn't have to stand for time, but it's a parameter. So in section 10.1, we learn just how to work with such things. So, to start with, we're going to look at number 8 on page 645. What we're given in number 8 is x is a function of t, it's sine of t, and y is also a function of t, 1 minus cosine t, and we are given that t goes from 0 to 2 pi. And the directions are, let's sketch the curve that's associated with this. Sketch the curve. And we're also going to use arrows to show the direction in which the curve is traced. Because essentially, since t is going from 0 to 2 pi, that has an idea of increasing. And as that happens, the coordinates that we're looking at, x comma y, are going to be moving along the curve. So we're going to sketch the curve and also show the direction in which the curve is traced. And then in part B, we're going to eliminate the parameter to find a Cartesian equation of the curve. Cartesian just means xy. Okay, so how do we sketch the curve? Just go back to when you first learned how to sketch curves, make a table of values. It's really as simple as that. Since I have trig functions here, it would make sense if we choose values for t that we've seen in trigonometry, pre-calculus, calculus 1, and now calculus 2, which would be things like 0, pi over 2, pi, 3 pi over 2, and 2 pi. When t is equal to 0, sine of 0 is equal to 0. So we get an x value of 0. When t is equal to pi over 2, x is equal to 1, because that's sine of pi over 2. When t is pi, x is equal to 0. When t is 3 pi over 2, x is equal to negative 1. And when t is 2 pi, then x is 0 again, because we're just using the sine function for getting our outputs for x. Now for y, we have 1 minus cosine t. When t is equal to 0, y will be 1 minus cosine of 0, and 1 minus cosine of 0 is the same thing as 1 minus 1, which is 0. When t is pi over 2, we get 1 minus cosine of pi over 2, which is just going to be 1. When t is pi, we get 1 minus cosine of pi. That's the same thing as 1 minus negative 1, which turns into 2. And then when t is 3 pi over 2, we get 1 minus 0 again, and then we just repeat at 2 pi. So as far as what a sketch looks like, we start at the origin, then it goes to 1 comma 1, and then it goes to 0 comma 2, and then it goes to the coordinate negative 1 comma 1, and then it ends up back at 0, 0 again. And as we should expect, this is similar to an example that you see in the video on 10.1. We essentially just get a circle. And how is this circle traced? Counterclockwise. It shouldn't be a surprise to us that we get something that is circular in shape, because we started with trigonometric functions, which are also called circular functions. So now let's eliminate the parameter and see how we get a Cartesian equation, something involving just x and y. And we can see how we get an equation of a circle. So how would we do that? Well, think of trigonometric identities. Think of x squared plus y squared is equal to r squared. And then think of the Pythagorean identity of sine squared t plus cosine squared t is equal to 1. That gives you a clue of how we could find something related to a Cartesian equation. So what we can actually do is this. X is equal to sine t, which means x squared is the same thing as sine squared t. Now we want something similar for cosine. We have that y is equal to 1 minus cosine t. We should actually then rewrite this as y, or actually I'm going to do, yeah, that's fine. Y minus 1 is equal to negative cosine t. And then we can square both sides. And we find out that y minus 1, quantity squared, is equal to cosine squared t. Notice that since we have sine squared as an expression and cosine squared as an expression, then we can find their sum using the Pythagorean identity. Their sum would just be 1. And so what we get is x squared plus y minus 1 squared equals 1, which is a circle with radius 1 and centered at the coordinate 0 comma 1, which is exactly what we see here. All right, so that's how we can just take x and y defined parametrically, sketch a curve, show directions in which that curve is going, and then also eliminate the parameter and just get a Cartesian equation for that. Let's look at another problem. Number 2 on the same page, page 645. A little bit simpler. We are given that x is equal to t cubed plus t, and y is equal to t squared plus 2, and t is going from negative 2 to 2. Sketch the curve. and indicate with an arrow the direction in which the curve is traced. So just like in the last example, I'm going to make a table of values. Again, t is going from -2 to 2. I don't have trigonometric functions, so I don't have to use anything with pi, but I could just choose -2, -1, 0, 1, and 2. That will probably give me enough. When t is equal to -2, x is -2 cubed, which is -8, plus another -2, so I get -10. And y would be -2 squared, which is 4, plus 2 is 6. For -1, x is going to be -1 plus another -1, which is -2, and y will be 1 plus 2, which is 3. When t is equal to 0, x is equal to 0 plus 0, but y will be equal to 0 plus 2. When t is equal to 1, x is equal to 1 plus 1, which is 2. Y is equal to 1 plus 2, which is 3. And then finally, when t is equal to 2, x is equal to 8 plus 2, which is 10, and y is equal to 6 again. So let's sketch this, and again, we can just think the coordinates that we get, x comma y, those give us a frame of reference as to where we are plotting our points, but we can think of the order in which those points came about. So the first point that we got was -10, 6. So that would be there. And then -2 comma 3, about there. 0 comma 2. And then we just go back onto the right side of the y-axis. We get a point at 2 comma 3, and then 10 comma 6. One thing that we definitely know is that it is going to stop at our endpoints, because that's as far as t goes. If you wanted to eliminate the parameter, you would want to get t by itself in one of these equations. It'd most likely be easiest with y equal t squared plus 2, and then you could substitute that into the other equation. All right, and then finally, let's look at one other problem. Number 15. This one we are given x is equal to t squared and y is equal to the natural log of t. We want to first, in part A, eliminate the parameter to find a Cartesian equation. So it's like the opposite of the first example we looked at. And then part B, sketch the curve and indicate with an arrow the direction in which the curve is traced. So really, very similar to number 8, just reversing the order of the directions. Okay, so eliminating the parameter means you don't want to see t. You want to find a Cartesian equation, something with just x and y. So you would like an equal sign, you'd like some x's, you'd like some y's, and you'd like some constants, but no other variables. That's the idea. Now I could certainly take x is equal to t squared and just use t as the square root of x. And then I could write this as, or I could write y as the natural log of t, which is the natural log of the square root of x. And we could think of that as the natural log of x to the 1/2, which would be 1/2 ln x. That is definitely one way we could do this. Y is equal to 1/2 natural log of x. But there is another way. If y is equal to the natural log of t, that means that e to the y is equal to t, which then we could plug that into t squared. X is equal to e to the y quantity squared, which really just means e is equal to e to the 2y. Either equation works. We just might be more familiar with, say, y is equal to 1/2 natural log of x. Okay, so now let's sketch a curve with this. Notice in this problem we weren't given anything with a restriction on t, but since we're talking about the natural log of t, this implies that t has to be greater than 0, because you can't find the natural log of 0 and you can't find the natural log of negative numbers. So as far as sketching what this looks like, the curve that we got here, y equal 1/2 natural log of x, pretty much already tells us what we're going to be graphing. And we can think that as t is increasing from something really close to 0 and then getting larger, that then influences x. So we're really just getting our y equal 1/2 natural log of x curve, and then it's just an arrow going in the direction we would expect. Since t is greater than 0, that means it's starting at small numbers and just increasing in a positive direction. That means we're going to expect a natural log curve that just does this. Where does it cross the horizontal axis? Well, you can think that when x is equal to 1, then y is equal to 0, and when x is equal to 1, that's when t is equal to 1. So no real big surprises there. So in the next section, 10.2, we then start doing things with these curves. Pretty much everything that we've done in Calculus 1 and 2 up to this point. We're going to find derivatives, integrals, areas, surface areas, arc lengths, all kinds of stuff that we have done with functions before. So in section 10.2, we start by learning how to take derivatives. And so if we have something like x is a function of t and y is another function of t, then if we want to find the derivative of y with respect to x, that really just amounts to finding the derivative of y with respect to t and then dividing by the derivative of x with respect to t. If we want to find the second derivative, we just remind ourselves that that means the same thing as the derivative with respect to x of dy dx, and that just means that dy dx is playing the part of y in this case, which means we take the derivative with respect to the parameter t of the first derivative, dy dx, because essentially that's already going to be a function of t anyways, and then divide by the derivative of x with respect to t. So first, I'm going to start with number 8 on page 655. Which asks us to find an equation of the tangent line to the curve at the given point by two methods, without eliminating the parameter and then by first eliminating the parameter. So we're given x is equal to 1 plus the square root of t, y is equal to e to the t squared, and we're given that the point is 2 comma e, so we want to find the tangent line to the curve at the point. So the first option is doing this without eliminating the parameter. So remember that the tangent line is going to be y minus y1 equal m times x minus x1. 2 is x1 and e is y1. M is the derivative at the point. So we need to find the derivative. That would be dy dx. That's going to be dy dt divided by dy dx. The derivative of y with respect to t is going to be e to the t squared, but then times the derivative of t squared, which is 2t. The derivative of, this is not dy dx, it's dx dt. The derivative of x with respect to t is just going to be 1/2 t to the negative 1/2. And we can simplify this by simplifying the fraction. Instead of 2 divided by 1/2, that's going to give us a 4. And the t to the first power divided by t to the negative 1/2 power will just be t to the 3/2 power. And then e to the t squared. So then how do we find the value of the slope? Well, we were given that x is equal to 2 and y is equal to e. When y is equal to e, that means that e is equal to e to the t squared, which means that t squared is equal to 1 because we're just equating powers at that point. Which means that either t is equal to 1 or t is equal to negative 1. But since we have square root of t involved in the equation for x, we can't use the negative value. So only t equal 1 allowed. So that means that our slope is our derivative evaluated at t equal 1, which would be 4, 1 to the 3/2 power times e to the 1 squared, which is just 4e, which is a little bit bigger than 10. So the equation of our tangent line is y minus the y value, e, equal 4e x minus the x value, 2. Which we could put into slope-intercept form. Y is equal to 4ex minus 8e plus another e that I added from the left. So we could say that. I'll leave it to you to eliminate the parameter because we just saw how to do that. It might be simple to take this equation and just write x minus 1 equal the square root of t, which means that x minus 1 squared equals t. And then you can plug that into y. And then you could use that to find your derivative, find the slope, and then write the equation of the tangent line. So there's an application of a first derivative related to parametric equations. Let's do a little bit of a higher level example. Let's find an area. This is going to be number 32, also on page 655. Find the area enclosed by the curve x equal t squared minus 2t, y equal the square root of t. So it's a curve defined by those two equations and the x-axis. Oh, sorry, actually 32 is the y-axis. So it might help us if we just sketch this curve, first of all. How do we do that? Plug in some values. Notice we see that y is the square root of t, so we can't have anything negative, but we can at least start at 0. So we'll go t equals 0, 1, 2, 3, 4. See where that gets us. When t is 0, x is 0, and so is y. When t is 1, x is 1 minus 2, which is negative 1, and y is the square root of 1, which is 1. When x is 2, we get 2 squared, which is 4, minus 2 times 2, so 4 minus 4 is 0. And then y is the square root of 2. When t is equal to 3, x is equal to 9 minus 6, which is 3. Y is equal to the square root of 3. And when t is equal to 4, x is equal to 16 minus 8, which is 8. And y is equal to the square root of 4, which is 2. We actually only need a little bit of this, because when this curve is traced, it starts at 0, 0. It goes to the left for x equal to negative 1 and y equal to 1. And then it goes back to the right to cross back through the y-axis. X equals 0 and y equal the square root of 2, which is almost halfway between 1 and 2. So we're doing some sort of curve like that. So the area that we're looking for is just this little part here. So now you could think of how you would have done this using Cartesian equations. You could think of x as a function of y, and then you're essentially just finding the area that is below the y-axis, really meaning to the left of the y-axis. But we're going to be doing this using the parametric equations. So there are similar formulas that we expect using integration. And you can find these in the textbook. If you look on page 651, you can see that if you're looking for the area below a curve, which we think of as y equal a function of x, you can see an equation related to that. And we're going to do something similar with this parametric curve. So the equation for finding area, or I should say the integral, is from alpha to beta g of t f prime of t dt. That's where if we were defining y as g of t, so you could also write this as y, and then f prime of t is just really the derivative of x with respect to t, and then dt. Same idea. So in our case, we're given y as the square root of t, and then dx dt, or I should say x prime of t, is just going to be 2t minus 2. So our integrand, y times x prime of t, is just going to be the square root of t times 2t minus 2. And that's just going to give us 2. Square root of t times t is t to the 3/2 minus 2t to the 1/2. So then the only thing that we need to figure out is, we know where the y values are, but what are the t values? Well, we actually already have that, 0 to 2. With this whole curve creates the boundary of the curve with the y-axis as long as we have t going from 0 to 2. So our area is just the integral from 0 to 2 of 2 t to the 3/2 minus 2 t to the 1/2. And of course we could factor out the 2, but it's going to get multiplied back in anyways. So this results in 2 t to the 5/2, but then I have to multiply by 2/5. 2 times 2/5 is just 4/5. Minus 2 t to the 3/2, but then I have to multiply by 2/3. 2 times 2/3 is 4/3. And then we evaluate from 0 to 2. Plugging in 2 to the 5/2 is the same thing as 2 to the, well, I should say square root of 2 to the 5th power. And then minus 4/3 square root of 2 to the 3rd power. And then, of course, when we plug in 0, we're not going to get anything. Square root of 2 raised to the 5th power just will turn into 4 square root of 2. And then square root of 2 to the 3rd power is just going to be square root of 2, or I should say 2 square root of 2. And we can get a common denominator here. Multiplying the first fraction by 3 over 3 and the second fraction by 5 over 5. And so what we're going to end up with is 48 square root of 2 minus 40 square root of 2, which is 8 square root of 2 over 15. Which we should expect. If we think of the shape that we see here, it's above the x-axis. And so we should expect, if we thought of this as y equal a function of x, which it isn't because it fails the vertical line test, but we could split this up, and then we could add the two areas, we would expect that it's something positive. All right, and then the last example that I want to look at is involving arc length. And this will be number 44 on page 656. Find the exact length of the curve. The curve is defined x equals 3 cosine t minus cosine of 3t. And y is equal to 3 sine t minus sine 3t. If you take a look at the arc length formula, you really start to see that what we were talking about back in chapter 8 actually looks pretty simple now in the scope of parametric equations. It just looks like the Pythagorean theorem. We see a square root of the sum of two squares. So our arc length formula is L equal to the integral from alpha to beta. These are going to be limits with respect to t of the square root of dx dt, or x prime squared, plus dy dt squared dt. And that's it. So we're going to find our derivatives and then square them. So for example, x prime is negative 3 sine t, and then plus 3 sine 3t. Y prime is 3 cosine t minus 3 cosine 3t. So x prime squared is the quantity negative 3 sine t plus 3 sine 3t squared, which would be 9 sine squared t minus, I'm going to have 2 times 3 times 3, so 18 sine t sine 3t, and then plus 9 sine squared 3t. And in a similar way, when we take y prime and square it, we get the quantity 3 cosine t minus 3 cosine 3t squared, and that's going to give us 9 cosine squared t minus 18 cosine t cosine 3t plus 9 cosine squared 3t. And we're going to add these because it's underneath the square root, the square of x prime plus the square of y prime. So we can notice a couple of things. If I add the 9 sine squared t plus the 9 cosine squared t, that gives me 9, because it's just 9 times the Pythagorean theorem. I also get another 9 from 9 sine squared 3t plus the 9 cosine squared 3t. And then I end up with minus 18, which I can factor out of the remaining two products. Sine t sine 3t plus cosine t cosine 3t. This part that's in parentheses here, this is another trigonometric identity. That's actually related to the difference formula for cosine. And this would be cosine of 3t minus t, which is just cosine of 2t. So what we end up with this whole sum that's going to be underneath the square root, reminding you of what we did in Chapter 8 of simplifying that whole thing before you even try taking the square root. We get 18 minus 18 cosine 2t. And we can actually simplify this a little bit further. Cosine of 2t, you might recall, is 1 minus 2 sine squared t. And so when I distribute my 18s, that whole expression underneath the square root becomes 36 sine squared t. All right. So we've simplified all of that. Which means then we can take our square root, which will be 6 sine t dt. And as far as our limits go, I actually forgot to write this down. This was given a number 44. T is running from 0 to pi. And I should mention, because of that restriction, sine is positive, as in the sine function is positive for t from 0 to pi, which is why I'm allowed to take this square root right here, and it becomes a positive 6 sine t. It depended on those limits. So then finally, Antiderivative is negative 6 cosine t. We're evaluating from 0 to pi. Cosine of pi is negative 1. That gives me a 6 minus cosine of 0 is 1. 1 times negative 6 is negative 6, and that gives me 12.